So first of all, let me thank Professor Shankaraman for inviting me to this webinar series. And I'm going to talk about physics and technology with the 2D materials. And I will tell about some of the work that we have done in this area of 2D materials. And towards the end, I will tell something about how this can be extended for the work in optronics, where I'm also actively looking for collaboration from the optronics community. So the work which I'm going to talk about is on 2D materials, and I will soon tell you what these 2D materials are. And these are the people who contributed, some of the past students and present students contributed to this work. And we started this area of 2D materials approximately 5-6 years back. And those who are interested in knowing about our work, you can see some of these publications. This is exclusively in this area of 2D materials. So now you all heard about, nowadays it's quantum technology, quantum materials, etc. So this is a hype. And right now, if you go to, Wikipedia, this is a source of information for everybody to quickly look at something. So there's a definition of quantum materials. This is given here. And you will understand that, there are many materials like superconductors, the materials with the magnetic order, or with electronic properties linked to non-generic quantum effects, such as topological insulator, Dirac electron systems, such as graphene. All these things will fall under the category of quantum materials. In that way, in one sense or other sense, many of us are working in this area of quantum materials. So the materials which are interesting to me is graphene, topological insulators, wild semimetals, spin liquids, etc. Out of which today I'm going to talk about a 2D material, which is a topological insulator. So some of you may not know about topological insulator. So let me just explain what this topological insulator is, just to, for the sake of continuity for this talk. See, we all know that ordinary insulator like diamond. So you have electrons fully occupy energy bands, and the next available electronic state is far away in energy. So this gap which is having between this valence band and conduction band is renders diamond or silicon insulating. So the topological insulators are a new material where the energy gap between the occupied and empty states is fundamentally modified due to spin-orbit interaction. So as you know that the spin-orbit interaction goes with Z to the power 4. So that means heavy materials are used for this kind of studies. So since spin-orbit interaction is very important, you will see many of the materials that is used for this topological insulators consists of bismuth, antimony, tellurium, selenide, etc. So now to look at what is a topological insulator, this is a new kind of a semiconductor that behaves like an insulator in the bulk, and it is conducting at the surface. See, for example, if I just take just an analogy, so please don't relate this thing directly. This is just an analogy. If I have a block, which is a wooden block, this is insulating. Now I wrap the surface with copper foil. So then this entity is like an insulator in the bulk and conductor at the surface. So I combined wood and copper foil. Now in a topological insulator, what is happening? Intrinsically in this material, the interior portion is an insulator and the surfaces are conducting, right? So it has got metallic surface states, and also it says protected metallic surface states. So this is coming, if you look at the band structure of this material, you have bulk conduction band, bulk valence band, and also you have surface states. And not only that you have surface states, the surface state also has a property that if you look at this state, you see upspin electrons. If you look at this state, you will see downspin electron. What does it mean? That means if an electron is moving in this direction, so this is the metallic surface state, is moving in this direction, if it has to go back, it should reverse its spin. So that means even if there are scattering here, it cannot backscatter, because if you want to, the band structure won't allow this electron to backscatter. And if at all it has to backscatter, it should change its spin direction. If you want to change the spin direction, I need to have magnetic impurities. In case if I don't have magnetic impurities on this surface, this electron will continue to move in this direction. Similarly, this electron, which is downspin electron, will move in that direction. So my interest in this kind of systems is because of this spin polarization in this material. And this is a very exotic material. And now for the last 1 decade, there's a lot of investigation that's happening in this material. So this is just to give you a feel about the band structure. This is done by angle dissolved photoemission spectroscopy. The single crystals are grown in our lab. And you see you have the bulk valence band, bulk conduction band, valence band. And you see this, this is the surface states, and this point is called the Dirac point, or this point is called the Dirac point, and this is known as the Dirac core. So this is just a very preliminary introduction to a topological insulator. So what I'm going to do is to play LEGO with this kind of 2D material. So 2D materials means graphene is a 2D material. All of you know that if I have a graphite piece, then I can, with a scotch tape, I can exfoliate layer by layer. So I'm going to play a LEGO with different kinds of two-dimensional materials like, graphene, hexagonal boron nitride, niobium selenide, molybdenum diselenide. There are a lot of materials available. So today I'm going to play a LEGO with this topological insulators, which are again exfoliable material. So the material which I'm going to talk about to start with is bismuth selenide, Bi2Ac3. The structure of Bi2Ac3 is given here. And this consists of several quintuple layers. And then these adjacent layers are connected by a van der Waals interaction. So because of that, you can break this, the layer, and then you can exfoliate them. So typically a unit cell consists of less than a nanometer. And then each layer corresponds to approximately 1 nanometer. You can have multi-layers and you can exfoliate them and make devices according to your convenience. Now, this is the band structure which I showed you earlier. There, if you look at the Fermi level of this material, the Fermi level is now into the Fermi level is in the bulk conduction band. What does this mean? Ideally, I wanted to have the Fermi level in this band gap. Now the Fermi level is coming to the bulk conduction band. That means, though I said that this is an insulating material covered with a surface state, my insulating material is also becoming conducting because my Fermi level is lying in the conduction band. This is because of the selenium vacancies. When I make this Bi2Ac3, if there are selenium vacancies in the system, there is a kind of a self-doping. So it is heavily n-doped, and then this Fermi level is getting into this region. Because of that, this is not a bulk insulating material. So we need to make a bulk insulating material for any of our studies. So what we do now in this bismuth selenide, if you take another compound called antimony telluride, there the self-doping is such a way that it is a p-type conductor. So then we start asking the question, suppose if you have a material with the bismuth, antimony, tellurium, selenide, can we tune the Fermi level so that the Fermi level is in the band gap? So we grow single crystals by Bridgman technique. And this is one such crystal that we have grown, bismuth 1, antimony 1, tellurium 1.25, selenium 1.75. So we started with the target of Bi1, Sb1, tellurium 1, and Se2. But after the preparation, it has come to this kind of a composition. And we make several such crystals, and each crystal takes around 15 days to grow by this Bridgman technique. And this particular crystal I'm showing because this is one of the best crystals that we have. And we do the compositional analysis by electron probe microanalysis, and we establish the concentration even to the second decimal point. And such a single crystal, if I look at the angle dissolved photoemission, you see that I don't see this bulk conduction band or the valence band here. I'm only seeing the surface state, and the Fermi level is within that band gap. So now I have formed the required crystal where the Fermi level is lying within the band gap. So, and if I just tell you about the X-ray diffraction of these things, you will see that you will see 003, 006, 9, 12, 15, 18, 21 peaks. So that means it's a 00L peak. So that means it's a complete two-dimensional material with this C-axis oriented. Now what I do, I mean, for any of this further studies to explore the physics or technology of these materials, you make devices by electron beam lithography. So the device which I would like to make is a silicon substrate and silicon dioxide on top of it. And we will exfoliate this material, which is called BSTS. In future, I will be calling this as BSTS because bismuth antimony tellurium selenide. So this BSTS is exfoliated here. And then it is covered with hexagonal boron nitride, which is also a highly insulating material. And then you make a contact to this BSTS on this side as well as that side. I have a source and I have a drain. And if I deposit gold on top of it and then connect to the ground, then I can apply a top gate, or if I connect a line here to the ground, it's a back gate. So that means I can do a top gating or a back gating. You all know about field effect transistors where you do the gating. So this is similar to that. Now, if I look at the device here, this is prepared by electron beam lithography. And this scale bar corresponds to 5 micrometer. And if you look at this is the flake which we are talking about. And then this is one electrical contact. This is another electrical contact. So this is the one which is used to pass current through it. Then if you measure the voltage across these two, you get the Hall voltage. And if you measure the voltage across these two, you get the resistance. And then this is the top contact. And if I apply a potential through this line, then I will be applying gate. So I can do all sort of study in this kind of a material. Now, making is not that simple. I mean, it's of course done with exfoliation by Scotch tape. You take a glass substrate and you deposit PDMS on top of it. And then with the Scotch tape, you exfoliate hexagonal boron nitride, and then you add to this one. At the same time, on the silicon dioxide substrate, I exfoliate BSTS, and then this is brought to each other under a microscope, optical microscope, and then you bring them in contact, then apply a sufficient temperature so that this HBN gets released from this, and finally you get this kind of a structure. And then if you remove this the glass slide, you see this. And this is all done in a glove box because moisture and oxygen should not be there. And we have fabricated the stages in a microscope that is kept inside the glove box. So that means the crystal is exfoliated inside the glove box, and then we make this transfer and then cover it with HBN, and we take it out for the lithography purpose. And we make several such devices, each time, each device looks with a different shape and size. The reason is that this is done by exfoliation, because if you put a Scotch tape and remove it, it just gets into an arbitrary shape. If I do a thin film deposition and then pattern it, then I can have a regular pattern. Since I'm doing this exfoliation, there are arbitrary shapes. But since I know the exact distance between the probes and all the dimensions are known to me, then calculating, or extracting the parameters from these things are not a big issue. So now I have this, different kinds of devices with the different lengths, widths, gated length, etc. So now we start looking at the physical properties of the system. So the first property, again, what we do, you make this device and then do a wire bonding to a chip carrier. And then this chip carrier is inserted into this holder, and the whole system is dipped into liquid, in a liquid helium system, so that you can cool it down to 2 Kelvin, and then you can do the temperature variation and do different kinds of measurements. So let me just tell you, the kind of results you're getting. See, for example, if you vary the temperature of this material, and then if you measure the resistance, you see that the resistance is increasing in the beginning, goes through a maximum, and then starts coming down. You take a second device, you do the measurement, again you see it goes through a maximum and then comes down. So now here, let me just make my first proposal that, earlier I told you that this is a bulk insulating material and the surface is covered with a metal foil. If that is the case, what happens at very low temperatures, and if you start increasing the temperature, what you're measuring is the metallic surface state, because it's metal. So as you increase the temperature for a metallic material, the resistance increases, and the resistance keep on increasing. At the same time, the bulk of this material is insulating, or a semiconductor with around 300 millieV band gap. The resistance of that semiconductor is when you go from high temperature to low temperature, it keeps on increasing. But suppose if the resistance of this bulk and the resistance of this surface is almost kind of becoming equal, then it reaches a point like this. And then onwards, the conductivity of the bulks takes care and the resistance goes down. So my first proposal is that, look, I have a topological insulator now whose surface is conducting and the bulk is insulating. People may argue, look, this is not the proof because there are different kinds of material which shows metal insulator transition. So this may not be the only proof. So then what we do, we go to the next measurement where we started changing the gate voltage. So you apply a voltage to the top gate and you start changing the gate voltage. So keeping the temperature of the crystal at 2 Kelvin, you see that the resistance keep on increasing. It reaches a maximum and then starts coming down. Here I would say that, look, why it is going through a maximum is that initially I told you that there is something called a Dirac cone, and the center of the Dirac cone is a charge neutrality point. And if the Fermi level is above this Dirac cone, it is an N-type conducting material. And if the Fermi level is below this Dirac cone, it becomes a P-type conducting material. Exactly at the Dirac cone, which is a charge neutrality point, the density of states are minimum. When the density of states are minimum, the resistance is maximum. So I would say that is the reason that it is going through a maximum. So then you may ask a question, how do I know this is an N-type region and this is a P-type region? We do Hall effect measurement. This is another device, for example, where we are applying back gate voltage, and there we vary the applied magnetic field at different gate voltages. Again, you see here, plus 10 volt, minus 10 volt, minus 30 volt, it gives a slope as if this is an N-type conductor. But if I increase the voltage further, and when it crosses a charge neutrality point, the nature of the charge carriers is just changing, and this is the P-type region. So this tells me that with all this set of experiments, this proves that I have a topological insulator crystal. So you need to be carefully listening to this, because I will at the end I will also be telling about the possibilities for the optoelectronics community, and where we have all these crystals with us, and if somebody is willing to interested in collaborating with the right experimental tools with you, we can do that. So in that sense, please follow this very carefully. Now let me just give you another example. You start varying the backgate voltage, and then the previous device, then you measure this the resistance of the sample. It goes through a maximum and comes down, and this is the charge neutrality point. Now what I do, I can convert this into conductance plot with the gate voltage. You see that there's a linear region here, another linear region here, from where I can calculate the mobility of charge carriers in the P-type region as well as the N-type region. So now I'm establishing that this is a topological insulator. And what is happening here? I have this Fermi level. When the Fermi level reaches this point, I am hitting this point. So that means the minimum conductance, because density of states is minimum. When my Fermi level is somewhere here, I have N-type conducting region like here. When I bring the Fermi level below this charge neutrality cap, I have this P-type region. So now by tuning the gate voltage, I am able to make a material P-type or N-type the way I want. So that is the beauty of this system. So then we ask this question. See, in a graphene, people found that they make PN junctions with by applying the gate voltage. So we ask a question, since we have a very ideal system now, can we make a PN junction with this concept with the topological insulator? So we went further. So prior to our work, there was no work on topological insulators looking at the junction properties. So we again started making several devices where we have a full backgate here, and this is the topological insulator, and then we have a local top gate. So look at here, this is the whole crystal, a flake, I would say, and this backside, if I apply a backgate voltage, then this entire region gets, I can make it to P-type or N-type. Similarly, I have a top gate, and if I apply a voltage in this top gate, I can make this local region P-type or N-type. So this is the idea. So you apply the gate voltage such a way that if you bring the Fermi level below the charge neutrality point, you will get a p-type region here. You apply the voltage such a way that if it is above the Fermi level, above the charge neutrality point, the Fermi level, then it's an n-type region. So we ask the question, can we make an NP junction or PNP junction or NPN junction with this kind of devices? So again, you know, in physics, what is important is reproducibility and repeatability. So we will not rely on a single experiment. We will make several kinds of devices and then come with the experimental results which are all matching with each other. So again, the idea here is moving this Fermi level across the charge neutrality point. Look at here. So what we did was we just made this kind of a device. And if you apply a proper voltage here, I can make this region n-type region. And if I apply a minus 15 volt here, I can make it into p-type region. So now I have a PNP junction. Similarly, by changing the voltages, I can have NPN junction. Or if I put the voltages such a way that I can make the entire material p-type, or I can make the entire material n-type. See, look at here, you know, this is a material where I am able to completely tune the Fermi level so that I can make at my will a complete n-type material or a complete p-type material or a junction of these materials. Look at the enormous possibility of such kind of a material. If I want to make a PN junction in a semiconductor like silicon, I need to have a p doping and n doping separately. Now, just by varying the voltages, we are getting PN junctions. So this is just to give you more information. Look at here, you start varying the top gate voltage, and then for a given back gate voltage, you get this kind of curves. And like this, for different back gate voltages, if you extract this curve, then finally I can make a two-dimensional picture where this is the variation of the top gate voltage and this is the variation of back gate voltage. So there are 1000 such graphs which is embedded into this one. Now I have a PPP region, NNN region, PNP region, NPN region. Now if I apply a top gate voltage of 0.5 volt and a back gate voltage of 12 volt, I will definitely hit a PNP junction. If I apply minus 0.5 volt to top gate and maybe say 2 volt or 3 volt of back gate, I will get an NPN junction. So look at the beauty of this. You are able to tune the properties of this material, and the optoelectronics community can even now start looking at the infinite possibilities that are now present there. So then, we do, not only this kind of crystals, I'm just showing you the different kinds of crystals we grow and the different kinds of properties we get. See, we grow, for example, antimony tellurium selenide. Here the bismuth is missing. And again, we start doping with different materials like, tin 0.01% we have doped. Again, we do this vertical Bridgman method to grow single crystal. Typically, a student takes around 15 to 20 crystals to get his final 4 or 5 good crystals. 15 to 20 crystals means 20 into 15, almost 300 days. He or she will be doing the crystal growth. I mean, without any break. You can understand all characterization, etc. So people put sufficient effort to get into that stage. So this is the X-ray diffractogram of these crystals. And this is a single crystal, again using a glove box, we exfoliate it and you do AFM to estimate the thicknesses, etc. Then you do electron beam lithography, then you do the chromium gold deposition, you do the wire bonding. Finally, your device is on the chip carrier, which is wire bonded. So let me just show some more interesting results here. You can measure the magnetoresistance of this sample as a function of applied magnetic field. And you see that in this crystal, as the magnetic field is increased, the magnetoresistance increases, then it starts showing some kind of an oscillation. Sometimes we can think, oh, it's some oscillation, some noise, something like that, we can discard. Or we can extract physics out of it. People have done this. And if I apply magnetic field perpendicular to the sample, then I see an oscillation. But when I apply parallel to the sample plane, then I don't get this oscillation. But these oscillations can give you a lot of information about the topological surface state in this material. So from this thing, you can subtract the proper background, and then you see that there is oscillations here. Not only that it has got an oscillation, so those who are working in this area will know that we have Landau levels in this sample. So you can plot this Landau level index like 22, 23, 24, 25, 26, 27 like that, and plot as a function of 1 by b. Then you get a linear plot, and that linear plot is hitting this intercept at 0.4 plus minus 0.05. 2 times of that is the Berry phase in this material. So this tells me that there is a pi Berry phase in the sample. So those who are not aware of Berry phase, don't worry about it. I just want to establish certain facts here. Only for that purpose I'm showing here. So the pi Berry phase says that it's a topological material. So this is another way of establishing that you have a topological material, right? This is tin doped antimony tellurium selenide. And now if I remove the tin doping, still I have this oscillations. And again, I have this pi Berry phase. This tells me that this is a topological material, right? So this topological material has got surface state which is conducting, and the bulk can be insulating. So now the interesting part which I wanted to tell you is that, see, if you take this antimony tellurium selenide crystal, and this is an N-type conductor. The moment I dope with 0.01 tin, it becomes a P-type material. And both give me pi Berry phase, topological material. In the earlier example, I told you that by applying gate voltages, I am tuning the Fermi level to make it either N-type or P-type. Now I have 2 different materials. One is N-type, other one is P-type. So now the experiments which we are doing is that we are exfoliating one on top of other, and we are looking at the junction properties of p-n junction properties of this topological insulator combination. So, I mean, very interesting results. You get the Hall mobility from this SDH oscillations, the oscillation which I showed you earlier called the SDH oscillation. You can extract the mobility of the sample. So it's a very good samples with a very good mobility. So then let me just introduce you to another material which is not at all studied well, which is called weak topological insulator. In the other topological insulator, I said that the bulk is insulating and the surface is conducting. But in this kind of a weak topological insulator, only the side surface is conducting. So the side surface gives you the topologically protected surface state, whereas the top surface is a gapped surface. It's a dark state, something like this. But what can happen if you have a small structure on top of it? Because when you do exfoliation, there will be half-covered surfaces. And it was shown theoretically now that these surfaces also exhibit topologically protected surface state, which I will prove now it is indeed the case. And then we have discovered a new material in our lab, which is a new topological insulator. This is from this BISE family, and the crystal is just BISE. So when we investigated the structure, we found that it has got a Bi2 Ac3 layer and another Bi2 Ac3 layer, and they are separated by a bismuth bilayer. So it is Bi2 Ac3, Bi2 Ac3, and a bismuth bilayer in between. And because of that, this is a BISE structure, and this also can be exfoliated. So again, the crystal growth, and we find that all 00L orientations available. We do high resolution TEM, and then we do Lave diffraction just to establish all the crystals which we make. We will establish that is a single crystal by different kinds of techniques. And my collaborator, Professor Umesh Wakmare from JNC ASR, did the calculations, density functional theory calculations, and this was predicted to be a weak topological insulator, and we did the angle resolved photoemission spectroscopy study, and that matches with our theoretical data, and then we established that this is a weak topological insulator. Now, the electrical property of weak topological insulators were not known prior to our study, because one of the crystals that has been shown to be weak topological insulator was this bismuth rhodium iodide, It's a very difficult crystals to synthesize, and it was very difficult to preserve the crystal without contamination. So that's what I understand from the literature. So now we have a stable compound, and we started asking the question, okay, now the theory tells us it is a weak topological insulator, and the angle resolved photoemission spectroscopy also confirms the theoretical results. So now we have a new weak topological insulator, BISC. So again, we make these flakes. As I told you earlier, we make these flakes. But here, unfortunately, the entire region it is conducting, this tells me that there is more self-doping in the bulk, and the bulk is also conducting. So that's why the carrier concentration is a bit high here. And we do then, magnetoresistance as a function of applied magnetic field. And from there, we can fit this conductivity data with this equation called Hikami-Larkin-Nagorka formula. And with this one, we can extract different parameters from this material. One important parameter is this alpha, and another important parameter is this L5. Alpha tells me how many conducting channels are there. Suppose if I have a topological insulator like this, and if there is one conduction channel and another conduction channel, I will get alpha equal to 1. And if I have alpha equal to 2, means this width is very small, and the top and bottom conducting channels are coupled to each other. So from there, we just calculate, we get alpha value as 1. So that tells me that 2 independent conducting channels are there. And the phase coherence length we extract from that data, and this is the temperature. Then we plot this as a function of temperature, and then we can talk about the conduction mechanism, etc. in this material. So now we have discovered a new weak topological insulator, and absolutely no study on optoelectronics part is done in this kind of a crystal. So, and what we do, we grow the single crystal, the thin films of this BISC films on silicon substrate by PLD. I saw in this video which was playing that you have this PLD system there. So we also grow these crystals by PLD at a different substrate temperature. And then we look at the AFM analysis, you get this triangle shaped thing at appropriate temperature. So we have a very good film, and we confirm the quality of the film by the Raman spectroscopy. See, the films grown at different temperatures. Finally, we have the data from the single crystal data, and we find that the optimum growth temperature is the one that gives me exactly same Raman spectra as my single crystal. And we get a lot of information from this Raman spectroscopy studies. So once we have this film, again, what we do the Hall measurements, we find out how many conducting channels are there, we calculate the L5, we calculate the mobility of this film, and you see here the magnetoresistance for a 25 nanometer film. See, the magnetoresistance gives very nice weak anti-localization, and here also you see the conductance delta sigma is calculated. And then from there, we use the HLN equation to extract all the good parameters of this material. And again, the number of conducting channels for thicker films is 2 channels. As you decrease the thickness to very low thicknesses like 9 nanometers, 15 nanometer, and the thickness is very low, and my top surface state and the bottom surface state start coupling to each other, and I get alpha equal to 1, alpha equal to half. That tells me it's a single conducting channel. Similarly, the conduction mechanism also varies as the thickness of this material changes. Now, we started asking the questions, it's a new system. Nobody has studied this kind of system. So can we do chemical doping like what we did for the tin doping in the previous case? Our idea is to make a bulk insulating material. So far, our attempts on bismuth selenide, and we also make bismuth telluride, we never got bulk insulating material because of the self-doping. So then we started asking ourselves the question, can we do compensation doping and then see whether we can get bulk insulating material? So we did copper doping, we did antimony doping, and maybe I will just describe one such experiment with 8% antimony doping. Again, we grow the single crystals and we start exfoliating the way I showed you earlier, and then we make devices out of it. Then again, unfortunately, this is not a bulk insulating material. It is like bulk conducting. but it has got very good surface states. But I would like to see, as time progresses, that I get a metal insulator transition in this kind of structure as well, so that we have the ideal crystal. But very interestingly, if you start applying a magnetic field as a function, the resistance as a function of applied magnetic field, we started getting now for this 8% doped, antimony doped BIAC, very nice oscillations. From there, we can subtract the background and we can get these oscillations. And this is called the Shubnikov-de Haas oscillation. And from the Shubnikov-de Haas oscillation, we can extract different parameters of this material. You can take the Fourier transform, and then, that reveals a lot of important information. You can calculate the effective mass of these electrons, which is only 0.142. It's like, Dirac fermions. The Dirac fermions appears to be like a massless Dirac fermion because you have this linear dispersion, but we get around 0.12. So the effective mass has come down drastically, and we can extract a lot of parameters. You can also fit it with this Lifshitz-Kosavic formula, and again you can extract different parameters. And here again you extract the Berry phase of this material, which is pi Berry phase. So this is a very interesting and excellent system where you have a lot of information that is coming. And again, we can put this Landau level indexing like 9, 10, 11, 12, 13, and you take this indexing and you extrapolate. Again, it is coming 0.47. So 0.45, 0.5 is Berry phase. This is 0.47. So it is again showing pi Berry phase, and this is the first establishment of 2D Dirac fermions in the system. So this is a rich variety of properties can be obtained here, and we can also look at the mobility. That is the most important aspect here. So when we did the Hall data analysis, we find that this material can be fitted with a 2-carrier model, and we find that there are hole pockets as well as electron pocket within the same material. And not only that, we get an extremely high mobility in our material, which is around 15,000. So which is the highest among any of the topological insulators so far. That is why we have not published it yet. We are just looking for further confirmations that, with the different devices, that it is a exact value. Then it's a major breakthrough because the carrier density is extremely high. So along with this, now we are also preparing different crystals to make it bulk insulating as well. So we started with a system which is a weak topological insulator. Theory as well as ARPAS data told us that it's a weak topological insulator. Then we looked at the magnetotransport data, and we found that it is a topological insulator. And then we started doping with antimony. Then we could establish pi Berry phase, which is characteristic of this topological systems, as well as we could enhance the mobility of this material to such a high value. So this is a very, very interesting system. Now the question is that what next? The what next is something that our group is not having any expertise, is the optoelectronic applications. See, as far as the Bi2 Se3 material is concerned, there's a lot of work that has gone in. People, if you look at this preparation approaches, this van der Waals epitaxy, which I was talking to you, and people are also making some kind of a solution synthesis. And then people are looking for different kinds of properties, the terahertz detection, UV-IR photo detection, then spin optoelectronics kind of thing. And, Professor Shankaraman told me that, this is a seminar on optoelectronics. So can you just bring in some optoelectronics component also in the talk? So I thought, okay, maybe this is the right time to advertise to the community working in the optoelectronics that this is a new material system which is not explored that much as many other systems, and there's a lot of potential that is lying here. And this is an example of Bi2 Se3 material, and I came across a review article very recently. This is just a week back, it's old, and I like that paper very much because they summarized many of the activities of 2D Bi2 Se3 materials for optoelectronics. So these are the different papers that is doing different kinds of study. This angle resolved photoemission spectra I showed you earlier. And then, people are looking for transmittance when they put this crystal on pure mica and ITO, and they see exciting, optical properties. And also people started making, this kind of photo detectors based on this Bi2SE3 flake. So they illuminate with, light of 1456 nanometer, and then look at the photocurrent in this kind of a structure. And they calculate the responsivity as well as detectivity with this kind of a detector. And this is an open area. See, look at here, this is Bi2SE3, pure Bi2SE3. I told you in the beginning the difficulty we faced with Bi2SE3 because it was not bulk insulating. Then we did antimony and tellurium doping, and we got it bulk insulating. So that kind of a structure, we should do all this kind of study. So the people who have the right equipments to do this kind of study can write to me, and we will look at if the proposals are fairly good, then we can look at a possible collaboration in this area. So similarly, people are making this like a flexible electronics, again, looking at, photocurrent and, very, very, very exciting and interesting area for the optoelectronics community. And BISC, I can guarantee you, it's an absolutely untouched arena. The first crystal was made by us for this topological properties, and we have made BISC crystals, we have made BISC films, we have made BIT crystals, we have made BISC films. Now we are making BI antimony tellurium selenide films that is showing excellent properties, and we are now in the process of making that single crystal. I would tell you that at least 15-20 attempts have been made so far by us alone, and we have not got the proper crystal yet. But it's an ongoing activity. I'm very hopeful in another 1 or 2 years. I mean, 2 years is a little too much, but it takes time. I mean, since we have already spent this much time, maybe in a year's time, we will be in a position to get that. And also, I found that, it's not only single layer. People started looking at bilayers, like, tungsten selenide with the Bi2SE3. And then they look at, different properties of this materials by shining with light. And these are the references, and so this can be derived, all this information can be derived from this particular reference. So with this, I will leave some time for discussion. So I just wanted to tell you that, these topological insulators are going to be the building blocks of future electronics because of fantastic properties that is coming. But of course, these are all not room temperature yet, it's all low temperature. But nowadays, people don't worry about low temperature at all. Even if things are working at low temperature, it should be fine. If you look at any MRI machine in any of the hospitals, it works at liquid helium temperature. But you get liquid helium there to run the MRI. So in that sense, we should not be afraid of using low temperatures. And also, I told you that the NPN junctions can be made out of the single TI. And also, I told you that we can make N-type or P-type topological insulator. And I also told you that we can extract a lot of interesting physics out of it. And I also told you that we have discovered a new weak topological insulator, which is BISC. And then we continue with BITE, then BISC, TI, antimony, etc. So we have plenty of thin films as well as single crystals. And also I told you that the doping of these materials is also bringing a lot of exciting results. So then in the last 3 transparencies, which I don't want to conclude, I was going through the literature and I found that there is a lot of exciting perspective for this optoelectronics community to jump into this area. And I'm quite hopeful that, we will be in a position to get very superior devices compared to the existing ones. And this is an area for future growth. So thank you for attention. This is my group last year. Before the lockdown, we took in front of the physics department. Thank you for your attention.